Earlier this month, astronomers observed a brief but unmistakable flash on the surface of the Moon, caused by the impact of a small space object that struck the lunar surface at very high speed. What makes this event especially significant is the fact that it was recorded live by a ground-based telescope, allowing for a rare real-time observation of a lunar impact. Initial analyses indicate that the collision may be associated with debris from the Geminid meteor shower, a widely known annual meteor shower. In this video, we'll explain what was observed, why this is important from a scientific point of view, and what this event reveals about the constant activity around the Moon. Let's begin. The impact occurred on December 12, 2025, at 3:09 a.m. UTC. At that instant, a small but well-defined flash appeared on the lunar surface and lasted less than a second. The phenomenon was recorded during routine lunar monitoring, carried out with a robotic telescope designed to capture rapid and transient events. The unique aspect of this observation is that the flash was seen exactly at the moment it occurred. In most cases, lunar impact flashes are only identified later, either through automated software or by detailed frame-by-frame analysis of recordings. This time, the observer perceived the phenomenon live on screen, something that even experienced lunar observers may never witness in their entire careers. The weather and location conditions were especially favorable for the detection. The impact occurred in the unlit region of the Moon during the new moon phase, when the absence of sunlight allows brief flashes to stand out clearly against the dark surface. Impacts on the illuminated part of the satellite are practically invisible from Earth due to the strong reflected glare. Initial analyses indicate that the object responsible was extremely small, likely only a few centimeters in diameter. Even so, it was traveling at a very high speed, on the order of tens of kilometers per second. Under these conditions, even a tiny fragment carries enough energy to produce a detectable flash upon colliding with the Moon. Based on the telescope's position and frame-by-frame analysis of the images, astronomers estimate that the impact occurred slightly northeast of the Langrenus crater, a prominent formation on the near side of the Moon. Determining the exact location will take time, as it involves analyzing the observation geometry, the accuracy of the time record, and possible instrumental effects. From an observational point of view, this detection is particularly significant. It is the first confirmed lunar impact flash recorded from Ireland, and only the second documented in the British Isles. Considering the size of the Moon and the extremely brief nature of these phenomena, this type of observation remains difficult to capture from Earth. Although the impact itself was small in scale, events like this have great scientific value. Lunar impact flashes offer direct evidence of how frequently small objects collide with the Moon, a type of information difficult to obtain through other observational methods. Unlike Earth, the Moon has no atmosphere to slow down or destroy incoming debris. Objects of all sizes strike the lunar surface directly, preserving the physics of impact. When a meteoroid collides with the Moon at high speed, its kinetic energy is rapidly converted into heat and light, producing a short-lived optical flash. By measuring the brightness and duration of these flashes, scientists can estimate the energy involved and infer properties of the impacting object, such as its approximate size and speed. When gathered over many observations, this data helps refine models of the population of small objects in near-Earth space. Geminid meteor shower, which takes place every year from early to mid-December. The Geminids are among the most intense and reliable annual meteor showers, known for their fast and bright meteors. What makes the Geminids unusual is their origin. Instead of originating from a traditional icy comet, they are associated with a rocky object known as 3200 Phaethon. This body behaves more like an asteroid, but releases debris when it passes very close to the Sun. Over time, this material forms a dense stream along its orbit. When Earth crosses this stream, we observe the Geminid meteors burning up in the atmosphere. However, Earth is not the only body that crosses this debris field. The Moon also regularly passes through the same region of space, making it vulnerable to impacts from this same population of particles. Preliminary estimates indicate that the impact speed was about 35 kilometers per second, a value consistent with the typical speeds of the Geminids. Although this does not conclusively prove that the object originated from the Geminid stream, the momentum and speed strongly support this interpretation. Events like this help validate theoretical predictions established decades ago. They demonstrate that meteor streams can, in fact, produce detectable impacts on the Moon, and that these impacts occur with measurable frequency. Over geological timescales, countless similar collisions have contributed to the Moon's heavily cratered surface. Importantly, this observation also helps to constrain the lower end of the meteoroid size distribution. Large impacts are rare and well studied, but small impacts are far more common and far more difficult to detect. Each confirmed flash improves our understanding of how frequent these small, yet energetic collisions are. Beyond their scientific value, observations of lunar impacts have practical implications, especially as interest in sustained activities on the Moon grows. Future missions plan to establish long-term infrastructure, including habitats, scientific instruments, and communication systems. Even small impacts can pose cumulative risks to exposed equipment. Understanding how often these impacts occur and what energies are involved is essential for developing effective protection strategies. This event also highlights the importance of continuous monitoring of the Moon. Advances in imaging technology, automatic detection software, and coordinated observation networks are making it increasingly feasible to detect impact flashes in real time. What was once a rare observational success may become more routine as these systems evolve. There is also the possibility of follow-up observations from lunar orbit. In some cases, high-resolution images obtained by orbiting spacecraft may reveal recent impact craters corresponding to the observed flashes. Although many impacts are too small to leave easily detectable craters, even the absence of a visible crater helps refine size estimates. From a scientific standpoint, lunar impacts function as natural experiments. Each collision excavates material beneath the surface, briefly exposing it to the space environment. Studying these processes contributes to a deeper understanding of how the lunar surface evolves over time. On a broader scale, events like this illustrate the dynamic nature of the Earth-Moon system. The Moon is in constant interaction with its surroundings, responding to the same debris flows that produce meteor showers on Earth. As monitoring efforts advance, astronomers will be increasingly able to associate individual lunar impacts with specific meteoric flows. This will allow for more precise mapping of debris populations and their interactions with planetary bodies. In the long term, systematic monitoring of impacts on the Moon may also contribute to research in planetary defense. Although small objects pose little direct threat to Earth, understanding the distribution and behavior of debris near our planet is a fundamental component in assessing the risks of larger impacts. This brief flash on the Moon was a direct, real-time glimpse of a process that normally remains invisible. It confirms that the Moon continues to be actively shaped by ongoing impacts of debris moving through the inner solar system. As monitoring improves, events like this will cease to be rare surprises and will become valuable scientific data.